So I'd like to take a look at comparing testing this with the vector signal transceiver and a traditional rack and stack box instrument in the demonstration.
Excellent. Let's take a look.
So here we're doing 64 test points, and with a traditional box instrument it took about 70 seconds to run through all the test points on this amplifier. Now here, right out of the gate with the vector signal transceiver and just using the embedded controller here, we're testing it at about 12 times faster without even using the FPGA.
So yeah, that's an excellent point. So we haven't even turned on the capability of the FPGA yet, and the PXI platform, which you see here that the vector signal transceiver is inside of, is simply taking advantage of the Moore's Law components that we talked about with regards to data buses, converters, and processor speeds. But now we're going to apply the FPGA and see what it can do.
This is the really exciting part. So up until now, users have had two ways to program the vector signal transceiver. So you've had the ultimate flexibility with the LabVIEW architecture that allows you to program it all the way down to the pins of the device. And this is an excellent way to program it, and it's been used by a lot of our users in many of those applications that I showed earlier. But then we also have another set of users that may be porting their code from existing RF instruments and want that compatibility and familiarity of industry standard instrument drivers. And those typically come with a closed FPGA. Now inevitably, these users, after using the vector signal transceiver for a while, want us to come back to us and want us to open the FPGA for them and ask, how can we take advantage of this powerful technology? So the great thing about the vector signal transceiver is that it's fully programmed in LabVIEW, so we can go ahead and open that up for them. And I'd like to show you what it would look like on the LabVIEW block diagram. Basically, you've got the traditional driver up here on the top, and then at the bottom here you can have an example modification. So you can still use the vector signal transceiver just like any other instrument and make those modifications.
So Eric, this looks like just standard LabVIEW code that you would see on a desktop. Is this the actual LabVIEW FPGA code?
Yeah, absolutely. So what you're looking at is the actual LabVIEW FPGA code. It hasn't been simplified or dumbed down or anything. This is actually what you get to use. So it's really that easy to make modifications and get up and running. And in addition, National Instruments has a number of pre-compiled FPGA personalities available for free at ni.com, so you can download them and get started with FPGA extensions right away.
Awesome.
So now let's take a look at applying this to our demonstration up here and see how that impacts test time. What we're going to do is take an FPGA extension and we're going to embed a serial protocol on the FPGA to communicate to the device under test via the VST's digital I/O port. And we're also going to embed a hardware test sequencer that's going to tell my vector signal transceiver what waveforms to generate, when to acquire the data, and it's going to tell it when to send commands to the device under test to change test modes. So let's take a look at what impact that has in the test time. So we're going to add the FPGA extension here to my device, to my code, and run it with the FPGA extension. And now we can see that before we had a 12x speed up, we now have a 60x speed up. So we've got another 5x in test speed time.
I would say that's pretty disruptive.
Yeah, that is hugely disruptive. So you really can see the power of the huge gains from moving the test sequencing down to the FPGA closer to the device under test.